For a lens, we combine Snell's law, the law of refraction, along with a spherical geometry to come up with this equation, the lens equation, thin lens equation. 1 over s plus 1 over s prime equals 1 over f. And f was a complicated function of the material of the lens and the radius of curvature of the two surfaces. Okay, so in a mirror, a curved mirror, if I have a curved mirror, let's go ahead and choose a mirror that's curved towards my object. Okay, now a mirror doesn't have, the light's not going through it, so we don't have refraction, but we have reflection. So if we combine our law of reflection along with our law of, our spherical geometry, we can come up with an equation that describes image formation for a spherical mirror. The cool thing about it is it looks just like this. It's the same thing. F is defined a little bit differently. It's actually quite simple. In this case, it's F is R divided by 2, the radius of the curvature divided by 2. Okay. We'll go ahead and focus on F as the focal point of this mirror, but it's what I think is just amazing is the different rules, Snell's law versus law of reflection, along with the spherical geometry, gives the same form of relationship between the object and its image. Okay, so what we're going to do right now is we're going to focus on how to determine signs here, and then how to draw and verify the positions we would get with this equation using ray tracing. So we have the same rules that we had with ray tracing for a lens, just now everything's on this side and we only have one focal point. Okay, so let's go ahead and assume that that focal point's right here. Okay, so first we have a parallel ray. Well, the parallel ray goes through the focal point, but now it bounces off the mirror heading on out. Okay, we have a focal ray. That focal ray goes through the focal point, and guess what? Hits the mirror, comes out parallel. And then to verify that I didn't mess up on those, I could do a central ray, which hits the mirror right there. And this optical axis now is the normal line, and the law of reflection says what the angle it comes in at, it goes out at the same angle. And that indeed verifies that that is the point where this image will form. Okay. Now the light really is forming there for this particular case, and so this would be a real image. Okay. Now we have some concerns. Well, is that positive or negative? It's on the same size as the object. But where's the light really existing after hitting the mirror? It's over here. So this is now the positive area for our rules of sign convention. So this is positive. This is a positive image. Where's the radius of curvature for this lens? Well, it's over here, probably about right there. It's in the positive area. The light's really coming in this area after bouncing off that mirror. And so it is also positive. So that rule still continues to hold true. Now the book and many books will describe that saying, you know, there's a different set of sign conventions for mirrors and for concave mirrors, convex mirrors versus diverging lenses and converging lenses. You can memorize all those if you want. But the main idea is you can use the single rule of after hitting the mirror or hitting the lens, where does the light go? That area is positive. Okay. All right. So with that done, let's go ahead and try a different example with a concave mirror. So this is the case. This is how I do it for my object outside the focal point. What if my object's inside the focal point? Okay. So let's say this is the focal point, and here's my object. Okay. Try and think about it the same way we did with the lens. It's just instead of going through, we come back. Alright, so I'm going to have a light ray that's going to hit this parallel, just like this one did, and it's got to go through the focal point. Okay, I'm going to have one come through the off the focal point, and then it's going to come out parallel. Now this is the same way as for that divergent case, where it's as if it came from the focal point. It's going to hit the mirror and come off parallel, like that. And then I would have one, that's my central ray, hits the center and comes off at the same angle. So as we've seen with lenses, these three rays are not converging on this side, and they're going to appear to converge over here. And so we get a virtual image, and it's on this side. This side is the positive side where light really is. This is the negative side, and so that is a negative image, and we can use that same rule to verify that.